Okay, welcome to the third session of our calculus class. And we'll get to the quiz in a second. I just want to make a quick little announcement. Next week, I'm thinking Wednesday, the quiz will probably be a proctorio quiz, base quiz, so that you can practice with the proctorio on the quiz, because the quiz isn't that important, whereas homework and whereas the exam, there's a lot of points in that. So just be ready, make sure that on Wednesday that you have a full computer with a webcam that you're working your quiz on. And that's really important, so that you can actually take it. And if it doesn't work, then you'll find out before the exam that you need to get a computer from the library or whatever, or deal with however you're dealing with it. And I'm here to help you too. So I figured I'd give you that little note, because that's kind of important, because it is going to be a proctored exam not tomorrow or anything, but in some weeks. So let us get to the quiz. So let me share my desktop. Okay, so here's your quiz. And the idea here is we have this graph, and it's this messy kind of piecewise defined graph, and we got to find some limits. So let's look at the first one. So the limit as x approaches -1 of f of x. So here's -1 right here. And what is the limit of f of x as x approaches -1? Yeah, it's 2. Notice if you go from the left or if you go from the right and you work your way towards -1, either way, you go towards 2. So that answer, part A, is 2. There's not a lot of work to show on these, but that's just the way it is. The next quiz will be a lot of work to show, as you'll see. Okay, how about the limit as x goes to 1? What does that little plus on top of that 1 mean?
From the right side.
Yeah, from the right side, and that's really important. Pay attention to the little symbols there. So as x goes to 1 from the right-hand side of f of x. So that means we're going to start on the right of 1, and then we're going to walk. And we're going to go along the curve and see what we go towards. And what do you go towards?
1.
1. Okay, so it's very important to note that little plus means go from the right-hand side. If the plus hadn't been there, what's the answer?
Does not exist.
Yeah, then it'd be does not exist, because the left and right are different. But since the plus is there, the limit is 1. So B is 1. C. Okay, so C is the limit as x goes to 2 of f of x. So now here's 2. And again, now you have to go left and right because there's no superscript of the number. And as you move towards 2, where are you going?
It looks like infinity.
Yeah, this goes towards infinity. So there's an asymptote here. So for part C, the answer is infinity. Any questions on that so far? Okay, and then part D is the limit as x goes to 3.
Does not
Okay.
exist.
Yeah, so notice if you go from the left, then you go towards 1. And if you go from the right, you go towards 3. And if you don't meet on the left and the right, then it does not exist. So part D is D and E. Any questions at all on number 1 for the quiz?
For C, do you just assume that it's gonna meet eventually? Because, I mean...
Well, it never meets, it goes up to infinity.
Oh, it just is, okay, at infinity.
Yeah, so that, it doesn't really hit. The infinity is not a number. Okay, it's just that That's kind of the idea. Let's see, answers. Yeah, I won't be able to see. I won't be able to see answers, by the way, until I get to grade it. So during lecture is not. I'm not grading the test, so I won't know until, you know, later, early afternoon or so, is when I'll probably grade it. So I won't know until then. So if you're wondering, you know, what it looked like on your quiz, I won't know until then. Sorry about that. Okay, let's look at question 2. Question 2 is, now we have f of x equals x squared for x less than or equal to 2, and 5x minus k for x greater than 2. Find the value of k such that the limit as x goes to 2 of f of x exists. Show your work. All right, so for the limit to exist, what does that mean here?
They need to meet.
They need to meet. So that means if I plug in 2 on the left, I should get the same thing as if I plug in 2 from the right. So the limit from the left, when I plug in 2, let me just write this down. So the left limit is just 2 squared, or 4. Any questions on that? Okay, what is the right limit? So what is the right limit? In other words, the limit as x goes to 2 from the right of f of x.
It needs to be 4 as well.
Okay, it needs to be 4, but what is it?
5x,
Based on,
5x minus k.
it's actually 10 minus k, because x is 2. Does that make sense? So it's 10 minus k, because we're taking x towards 2. That means we plug in 2, but if we're going from the right, that means we plug in 2 to the bottom one. That's how piecewise functions work. Now, for the limit to exist, that means the left limit and the right limit must be the same, because as you go from the left and you go from the right, you're supposed to meet. So the idea here is 4 is equal to 10 minus k. Very easy algebra, but you have to know what to do. So what's k?
6.
K equals 6. Okay, and there was a question, can you retry the quiz? And the answer is not as a regular quiz. I mean, you can always look at it again and try it again, but you don't get points for that. Well, and there's a bunch of reasons. One is the quiz. That homework is, you can retry homework. The quizzes are supposed to be getting you ready for the exam a little bit, kind of get a feel for what an exam looks like. And the exams look more like the quizzes, where you have to do it, you submit, and you commit, and you can't change your answer. Okay? The other reason is that if I let you try the quiz and let you try again for points, why would you all get it right? Why would you all get 100%?
Because you show us how right after.
Like, give you the answer right after. But I can't just let you redo the quiz. You just write down what I wrote. Okay, so sorry, you don't get to redo the quiz. But homework, you get to, retry. So homework's different. Homework is practice. Homework is practice for the learning. Quiz is a practice to get ready for exams, kind of see what exam problems are. And then the exam itself is going to be like a whole bunch of quiz problems. That's kind of how things are going to look. Any other questions? Any other questions? Okay, let's get to new material. That's over here. Okay, so what we've already seen is visually, you could look at a graph. Hopefully you were able to do that in the quiz and be able to kind of get a good feel for what the limit is, just by kind of looking from the left and right. Okay, and that's nice if there's an easy graph, but again, it's kind of guesswork because visually it's hard to tell. Sometimes it's easy, sometimes it's not. We want to be able to do things not just kind of visually, but we want to do things systematically with algebra. And that's kind of the plan of the day. Before I do that, are there any questions about anything that kind of, you need to get now, like homework or whatever, that you can't wait for office hours? Any questions about anything else, or about how the class is going, or anything like that? Any questions? Okay, if there aren't questions, then I'll move on, and we're going to be doing, like I mentioned, pretty much algebra today, as we'll see, and trig. Okay, and I have some examples, and I'll make some more. So, as I mentioned, the problem with doing it graphically is kind of a guess. Okay, it may look like there's a limit, but really, you just didn't look right, and that's the problem. And same thing with tables. Okay, tables can trick you also. Maybe the 10 numbers you plugged in all gave you something very similar, but that's because you were doing it too sequentially or something. But when it came down to it, the limit may not even exist. Okay, there's all kinds of things that can happen really close, and sometimes that happens. And I'll give you an example where that happened for most of human existence. Is that we thought things worked in a nice, easy way, Newton's laws and all that. And then Einstein found out they were wrong, okay? That he was just not looking enough, okay? Or people weren't looking enough, that there was actually more to it if you looked real close. And then even worse, there's something called quantum physics. And if you look really, really close, like at the electron level, the whole world goes away. So if you take the limit literally as your viewing perspective goes to 0, you can't even, it is just scary what's going on. And I can't get into it, but I will tell you, the limit of where an electron is doesn't even exist. Is that weird? So there's all kinds of stuff where you got to be careful about just viewing a graph and saying, well, I looked nearby and it looked good. That's all right, but it's not perfect. Yeah, Newton's laws don't apply perfectly. Okay, it turns out. Newton's laws are great for estimating, but they're not good for exactness. Okay, there's all kinds of issues. And again, I can't get into that because that would take, probably 2 years of doing math and physics. So I'm not going there. But I will let you know that when you take a limit in terms of looking at really close, then things are very different. Or if you take a limit, for example, when you go really fast, everything changes and Newton's laws don't work anymore. So I'll let you know that happens. Okay, and there's all kinds of other things with limits where things could go wrong and wrong badly. Black holes are an example. You take a limit as you reach what's called the Schwarzkopf radius. All of a sudden you get what's called a singularity and the limit doesn't exist anymore. Okay, and it's just really tough. So things happen with limits. Okay, but the good news is the main limits that you really need for most things, most people don't really care about black holes, but for other things like instantaneous velocity, algebra works. So we're going to be dealing with algebra, and we have this beautiful limit law, which I'm going to state in kind of easy tone, and that is the following. If the limit as x goes to c of f of x and the limit as x goes to c of g of x both exist, okay, you have to have them existing. If they don't exist, it's over basically, okay? And algebra is done in combination. And by the way, when I say algebra, I mean algebra and trig, so, or anything else that's like algebra, and it's done in combination. The limit passes through the algebra. Okay, that's, if you want to see the more rigorous full list of all the algebra properties, I'll let you look at the book. And it says that you can do all the things you want to do with algebra. And I'll show you how an example looks, and then you get the idea of what I mean. So let's suppose that we know that the limit as x goes to 2 of f of x equals 3. and we know that the limit as x goes to 2 of g of x is equal to 5. Then the question I have is, what if you want to find the limit as x goes to 2 of the natural log of 2 times f of x minus g of x over f of x squared? Okay, so the first thing, by the way, if either f or g didn't have a limit, then all bets are off. Okay, or the other thing is that if this algebra-wise didn't exist, like if the limit of f of x as x goes to 2 is 0, you got a problem because you got a 0 in the denominator and all bets are off. So as long as the algebra works nicely, and as long as the limits are nice, then you could do what you want to do. So what would you want to do to find this limit? What do you think might work? And the answer is, it will. So hopefully what you guess is actually going to work. What do you think we want to do to find this limit? Because we can't graph it, because we don't know what the graph of f of x or g of x look like. Yeah, we just do algebra. We just
plug in.
Yeah, we just plug in, and that's what this big limit law says, is that as long as there's no issues, so as long as the limits exist and there's no issues in the algebra. Okay, so for example, if we plugged in and we got log of negative something, you should worry a lot because you can't do that. But let's play. Certainly the limits exist. 3 and 5 are numbers, and let's just plug in ln of 2 times 3 minus 5 over 3 squared. And this works. Isn't that wonderful? So if you could plug in and it works, then plug in and let it work. Sound good? And that's the big theorem. Okay, I'm not proving this today. Probably never. Okay, I know how to prove it, but again, this is calculus and not real analysis. Real analysis, if you become a math major, that's the class where you prove everything. We're going to do a little proofs coming up, but not today. But we could do it, and it feels good. All right, now I'm going to do something that may not feel good because you might have forgotten your algebra, and that is negative 2 ln of 3. All right, what did I just do? See how your algebra is? And arithmetic. Anyone see what happened? It's not magic, by the way. Let you look at it. And I probably do things a little faster in my head than you might, because this is what I do for a living. Yeah, so the first thing, the numerator becomes a 1. Hopefully you all know that 2 times 3 minus 5 is 1. That's not supposed to be hard. And then we had a rule that we have now natural log of 3 to the negative 2, and the negative 2 can get pulled out to the left of the log. Remember that algebra that happened? Okay, it is important that you got that algebra down, because all that stuff is going to happen in our class. So today is kind of the first day where all that algebra you once learned must come back. And there's going to be a lot of that in this class. Okay, whereas Monday and Wednesday, there wasn't that much algebra. Now we got algebra in a big way, in a deep. Any questions at all on using the big limit laws? It basically says you can just plug in, hope it works. If it doesn't work, then you got to do more stuff. But if you plug in and you get nice numbers, then it works and you're done. Okay, it's kind of like with graphing. You look at the graph and it goes towards the number nicely in both directions, and you write it down and you're done, and that's the answer. Well, with with limits algebraically, then if you plug in and you get nice numbers, then it works and you're done. Any questions on that?
Quick question, Larry. It's
Sure.
-2 because it was in the denominator.
Yeah, so you have 1 over 3 squared. Do you see that?
Yes, I do.
And another way of writing 1 over 3 squared is 3 to the negative second power. Do you remember that in, it's kind of the definition of a negative exponent?
Yeah, it's slowly coming back. I do recognize that.
Yeah, yeah. And I expect that all of you had this, and that doesn't necessarily you can jump into it immediately and just get it without being helped, but it needs to come back. Because we're going to be doing a lot of algebra, and that algebra needs to come back so that by the time you take the test, you'll be able to do all this kind of algebra.
So the -2 power goes into the front of the natural log.
Yeah, that's one of what's
Okay.
called the rule of logarithm, the exponential
Okay.
rule of logarithms. It happened in algebra. Doesn't mean you remember it, but it did. I promise. If not, then I need to talk to your teacher because this is taught in every algebra class and in pre-calc too. It's kind of redone in pre-calc, but it's definitely done in algebra too. Okay. And with the high school now, they have all these different names for the algebra than these. Because now they have a 1, 2, and 3. I think it's just 1 and 2 or something. It used to be called intermediate algebra. Now it's called something else. But it happens. Any questions at all on this example? Okay, and I want to give you a warning. The hardest part of calculus, I said it on the first day, is algebra. Okay, the calculus ideas are actually not that hard. The algebra is hard, and you have to know to do it without being told. That's the hardest part. Okay, let's do some more examples. Okay, and this first example is very nice because it worked beautifully. So we want the limit as x approaches 0 of 3x squared minus 5x plus 4 over 7x squared plus 2x plus 1. And I want to give you a moment and see if you can get this. This is very easy. That's a hint. Okay, good. We're getting a couple good ideas. And the idea is you should always plug in because that's the algebra idea. That's these limit laws is that you're allowed to try. And as long as things are nice, you smile and you say, I'm done. Does that make sense? And if you plug in, what do you get in the numerator? 0 minus 0 plus 4. I hope you can do that without a calculator. And you get 4, right? What do you get in the denominator? 7 plus 0 plus 0 plus 1. And that's 1. 4 divided by 1. I hope you don't need a calculator for that either. That's just 4. There's really not much to show here. Any questions on this example? Okay, now let me go through the next example. Okay, so the next example is a limit as x approaches 2 of 3x squared minus 11x plus 10 over x minus 2. So what's the first step you should do? Very first thing.
Substitute.
Yeah, plug in. What do you get when you plug in on the numerator, and what do you get on the denominator? Yeah, so there's issues. You get 0 over 0. I'm going to write 0 over 0. In fact, it's not quite equals. I'm just going to go maybe over here. It's not equal to 0 over 0, and there's a reason. We'll talk about that in a second. That's what we get when we plug in. Why are we not done?
Zero can't be a denominator.
Yeah. And so 0 over 0 does not exist. Does that mean the limit does not exist? Yeah, it does not mean the limit does not exist. Okay, because remember, let's go back to the idea of the limit. Is the limit is not what it is at the value. It's what it is near the value. And if you're a little to the left of 2 or a little to the right of 2, you don't get 0 over 0 anymore, do you? Okay, so you can't just say I got 0 over 0 so it doesn't exist. That's just wrong. Okay, what it means when you get 0 over 0, what it means is the following. It means do algebra. Okay, and sometimes that's trig, by the way. So it means we need to do some algebra. Okay, and this is an example where you look at this and there's not a lot of choices. If you have a polynomial, what's the only algebra you can try to do? In one word. Yeah, factor. All right, so I want to tell you something, and this is very important because it'll save you a lot of time. You spent a lot of time in algebra learning how to factor, right? Do you remember that? And you had methods, whether you do the diamond method or the AC method. There are all kinds of guess and check method. I don't know if you remember all those different methods. None of those methods are needed. How come?
Because you're about to teach us a way easier method.
Yeah, but you've already learned it. You learned it in algebra. And it's called the fundamental theorem of algebra. That's how important it was. I don't know if you remember it. So what I'm going to do is I'm just going to copy and paste this guy so I don't have to redo the whole thing. All right, so the idea here is we want a factor. So I'm just going to erase all this. But one more time. But the fundamental theorem of algebra says that if you have a root, right? We plugged in and got 0. Then that is a factor. You always get if you always get a root, you get a factor. It goes together. It's all part of the big theorem. You don't need to factor by grouping or any of that kind of stuff. We know that x minus 2 is a factor. Just write it down. Because 2 is a root, so x minus 2 is a factor. And then you just look to see what you need. Well, to get a 3x squared, I need a 3x. And to get a plus 10, I need a minus 5. And you're done. Do y'all agree that was a whole lot easier?
Yes.
So as soon as you know a root, which you always do when you're doing these limits, because if it's not a root, if it's not a 0, then you don't have to do any of this. You just plug in, you're done. Okay, so the good news is that in every case in this limit stuff, the factoring will be this easy because you always know that's the root. All right, now we look at x minus 2 times 3x minus 5 over x minus 2, and what can I do?
Get rid of the x minus 2 because
Yeah,
they cancel out.
Exactly. And it's always going to be nice, but you have to be ready to do the nice. Okay, you could beat yourself up if that's your way of doing things, but I don't do that. I'd rather say, hey, I know that x minus 2 is a factor, so therefore I can just write x minus 2 and then just kind of realize I need a 3x squared, so it's 3x. I need a 10, so it's negative 5. And now I can I can cancel the x minus 2. If I cancel the x minus 2 in the denominator, what does it become? I'm saying this is, Yeah, it's 1. I know some people have trouble with that. I don't know why, but okay, don't make it 0 when it cancels. All right, so here's something very important. As soon as you cancel, it's time to plug in again and try and cross your fingers and hope. That usually works. So now if we plug in, what do you get?
1.
1, right? 3 times 2 minus 5 is 6 minus 5, which is 1. 1 divided by 1 is 1, and I'm done. And I just found the limit. Any questions? Any questions on how this works?
Would you ever have to cancel the original x minus 2 on the limit itself, like the 3x minus 11x plus 10? Would you ever have to cancel the limit, the x minus 2 on there as well, or never?
Maybe I'm not following. I did cancel that bottom x minus 2, and I don't see another x minus 2.
Well, like as at the starting limit, like the starting factors starting equation, that's what I was thinking. But
Well, there's an equal sign. So that x minus 2 just got copied.
okay.
And it gets canceled eventually. It just took a while to cancel it.
Got it.
I had to do some work to cancel it, but no, I did cancel it. Yeah, and and the good news is that whenever you have a rational expression, that means a polynomial divided by polynomial, and you get 0 over 0, you're always going to be able to cancel the factor. Okay, that's all part of that fundamental theorem of algebra. So this will always work. Okay, is that an approximate solution? No, this is an actual solution. And again, I didn't prove the theorem here, but that's this big theorem, the limit law theorem, is that I can always do that. Okay, notice, by the way, even though I have 0 over 0, it's not a problem. That does not, even though 0 over 0 does not exist, it's not a problem, okay? Because you're not at x equal 2, you're near x equal 2. How did I get 3x minus 5? Okay, so what I did is I wrote down the x minus 2.
My question was actually, how did you get 1 from 3x minus 5?
At the very end?
Yes.
Oh, x goes to 2.
Mm-hmm.
So I plugged in 2.
Oh, okay.
And if x
Cool.
is 2, I get 3 times 2 minus 5.
Thanks.
Yeah. Yeah, it's one of those where it's really easy, but it's also easy to just miss what I just said. So it's good that you asked the question. That's important. Okay, so the idea is that even though this is 0 over 0, and you think, oh, it doesn't exist, but it does exist because the limit is not at the value, it's near the value. And if you're near 2, there's no problem with the polynomial, with this rational function. Okay, if you're at 2, there's a problem. But if you're near 2, there's no issue, and that's why I'm allowed to do this. Okay, let's look at the next example. And so take a look at this one. What's your first step?
Plug in.
Plug in. What do you get when you plug in?
0, 0, or 0 over 0.
Yeah, if I just going to copy and paste, so I'm going to type it again. It's 0 over 0. It means we need to do algebra. Any questions on that? Right, if you plug in x equals 0, you get root 5 minus root 5. That's certainly 0. And the denominator, if I plug in 0, it's certainly 0. So that's 0 over 0 again. 0 over 0 is bad. It means we got to do algebra. Any questions on that? Okay, so now we got to think about some algebra we got to do. Can we factor?
Yes.
One more guess?
No.
No.
No, no, no. Sorry.
No, it's not a polynomial. Only polynomials factor. There's roots. Roots are not nice. Yeah, factoring's not going to work. So what we did in the last example will not work on this example. Okay, but we're still gonna do algebra, but you just gotta come up with the algebra. And this is something that unfortunately high school teachers almost teach it wrong. Okay, and it doesn't mean they do wrong math, but they teach the wrong thing. When you're dealing with simplifying roots, what you usually get in algebra is how to rationalize a denominator. Does that sound familiar? Okay, so I want to let you know, rationalizing the denominator is useless and historical. Okay, what do I mean by historical? Anyone know? See, I know because it was happening when I was a kid. Anyone know what happened when I was a kid in terms of math? Anyone know? Okay, so when I was a kid, something new came out called a calculator. And calculators changed the world, and it also changed algebra a bit too. So in the old days, it was really important not to have a root in the denominator. It turns out though, rationalizing the numerator, manual calculator, no, electronic calculator. Not a slide rule. Slide rule was before my time, actually. So electronic calculator came out just when I became a kid, basically, when I first learned math. So I was like the first one ever to have a calculator. And now you don't need to worry about a root in the denominator. On the other hand, rationalizing the numerator is very important for calculus. So I think that as a kid, when you learn algebra, you should learn about rationalizing the numerator because that's actually useful. The denominator is useless, just to let you know. Okay, so in particular, we're going to rationalize the numerator. So now you got to remember a little formula from algebra. And that, again, algebra is like really important. And that is that A minus B times A plus B. What is that? What's A minus B times A plus B? That's one you're supposed to have memorized. How does that simplify? A minus B times A plus B is, see y'all jumping in. Hopefully you can hear me. It got quiet all of a sudden. Are you still there?
I think we hear you. We just don't have an answer.
You don't remember? A squared minus B squared. Does that sound familiar?
Isn't it difference of squares?
Yeah, that's the difference of squares. A minus B times A plus B is A squared minus B squared. So what it does is that if you have an A minus B and you multiply by an A plus B, then you get to square A and B. Why do we want to square in this case, in our example here?
Get rid of the square root.
Exactly. So what I'm going to do is I'm going to multiply the numerator and the denominator by A plus B, or in particular, by root 5 plus x plus the square root of 5. And if I do it in the numerator, see if I'll let me do it. No, it didn't. So I'll type it out. Then I got to do it in the denominator also. Any questions? Any questions on what I just did there?
Larry, is that also known as multiplying by the conjugate?
Yep, that's multiplied by
Okay.
the conjugate root. Exactly.
Okay, okay.
That's another word for what I just did. Okay, so now let's simplify. Again, this is the top is a minus b times a plus b. So the top becomes very nice. So the top becomes a squared minus b squared. Well, a squared is just 5 plus x. And b squared is just 5. Any questions on that? Look at that numerator. It's beautiful. What does it become?
Just x.
Yeah, isn't that wonderful? And now, what do you see? What can I do? Which is wonderful again.
You could square it.
Can't square it. There's something I can do that's really nice. What do you see there? Something very simple. That's a hint. Very, very simple. Look at the beginning of that expression. Yeah, I can cancel that x over x. X over x is just 1. So the x over x goes away. Okay, remember what I told you to do right after you cancel? With limits, what do we always do after cancel? We plug in. Now plug in, and what do you get? One on the top. And what does the bottom become? What's the denominator? If we plug in x equals 0. Not seeing 25. See, if x is 0, then inside this first root is going to be root 5. Then I just have root 5 plus root 5, and that's 2 root 5. So I just get 2 root 5. Not 5 squared. 2 times root 5. There's a difference. And my answer is 1 over 2 root 5. And there's my limit.
So Larry, 1 second.
Mm-hmm.
So at the very beginning, when you multiply by what the numerator is for both the numerator and denominator, so the original equation is root 5 plus x and then minus root 5. And then after that, you have root 5 plus x plus root 5, unless that's just my screen. I don't know.
No, that's correct. And
is that what you're supposed to do?
Yeah, and here's why. The reason is, and this is what I was saying, is this is the difference of squares formula. And the difference of squares formula says that a minus b times a plus b equals a squared minus b squared. Do you remember that formula? That's a really important formula.
Yeah.
So what this does by multiplying by root 5 plus x plus root 5 is it squares both of those square roots. Because what makes this hard is the square roots. And the best way of getting rid of a square root is to square. This is the way we square, and it's the only way that you can actually square. Nothing else will work. You're allowed to do it. You're allowed to multiply by something over itself because that's multiplied by 1. That's always legal in math, is to multiply by 1. So what I did is I just multiplied by 1, but I multiplied by a nice kind of, maybe messy looking representation of 1 so that I end up with the a minus b times a plus b. Does that make some sense?
Yeah, that makes sense now. Thank you.
Yeah. Okay, and I am going to let you know, I'm not just like doing some random algebra. These are the key algebra pieces for this section. Okay, when I'm done, I have a third one to do, and those 3 do all the algebra you need. Okay, those are the main algebra. Any questions on these examples so far? Right. Very different than limits at using graphs, right? Okay, this does it with algebra. And these are, and the nice thing is this isn't guesswork, this is a proof. We know for sure this is a limit because I'm allowed to do algebra. That was the theorem. Okay, let's do the third one. A little bit more algebra. What's our first step? We have a limit. Maybe I'll make this bigger. So we have a limit as x goes to 0 of 1 over 3 plus x minus 1 over 3 divided by x. What's the first step?
Plug in.
Yep, plug in. What do you get when you plug in?
0 over 0.
0 over 0. Okay, so we get 0 over 0 again. 0 over 0 happens a lot. So I'm going to copy and paste this do algebra thing because that's what we're going to do again. So we get 0 over 0, that means do algebra. I want to let you know I'm not just being mean and just giving you a bunch of 0 over 0s just to be evil. Why is this going to happen for, I'd say, 80 to 90% of all examples you ever see for limits? You're going to get 0 over 0. You don't know why? Here, think, and the hint is think Monday. Monday's lecture, 4 days ago.
Is it
And that's
because
all.
it gets super, super close to it, but it's not exactly on?
Not quite. Think, what did we do Monday? It's what we did Monday. That's the hint.
So we actually have to do work and we just don't plug it in.
Thank you for getting what we did Monday. We didn't do limits Monday. What did we do Monday?
We did slopes.
We did slope of a tangent line, remember? And the slope of the tangent line, if you remember, that came from looking at the secant line and letting it get closer and closer. But the thing is, the rise and the run will always go to 0 over 0. Because if you let the 2 points get really, really close to each other, guess what? The rise becomes 0 and the run becomes 0. Does that make sense? Okay, so I'm not just being mean to you. It's just, this is what almost just about always happens, is that you get 0 over 0 whenever you're doing the slope of the tangent line, because the rise becomes 0 and the run becomes 0. So the rise or run becomes 0 over 0. And that means you got to do algebra. So that's where this is, that's the reason. Okay, again, I'm not just like in a bad mood this morning and giving you all these terrible hard problems. Why can't we just get the ones you plug in like the first one? It just was nice. But the 100% of the time when you're doing slope of the tangent line, which is what this class is all about, by the way, you get 0 over 0. So that's the bad news. All right, but the good news is that we can do algebra and it'll work. Okay, and it'll always work. That's the good news. Bad news is, the other bad news is that if you weren't paying attention in high school or in college when you took pre-calculus, then you forgot all your algebra and now you're screwed. Okay, but hopefully it can come back if you forgot some of it. So what algebra am I going to do on this example? And you've seen this in algebra classes. Yeah, the rise over run is 0 because it's a single point. It becomes a single point, so there's no rise and no run. You get 0 rise, 0 run. That's the reason why you always get 0 over 0. But with the algebra that you learned in your basic algebra, forget the limit stuff. If they said simplify this, that was what they told you in algebra, then what did you have to do? This one doesn't factors when you have like x squares and x cubes. Remember that? So it's not a factor.
Multiply by its reciprocal, or actually not.
Multiply by the, not quite reciprocal. You might have it in your head right, but your words are wrong. Multiply by the, starts with a C.
Conjugate.
That was with the roots. Common denominator. Okay, so what I'm going to do is I'm going to multiply top and bottom by the common denominator. Do you remember doing that in algebra? If not, do you believe me it happened in algebra? Because that definitely happens. So what I'm going to do now is I'm going to multiply that by the common denominator. Whoops. There. That's better. So the common denominator is 3 plus x times 3. Is that clear? And then, you know, that's it. Whenever there's like no common factor, the common denominator is just a multiple. You just multiply the two denominators. And what you do on the top, you got to do on the bottom. Okay, I want to give you a word of advice for calculus. And that is when we're doing this multiplying by the common denominator or anything actually, don't try to multiply the denominator through. Just leave the denominator as is. Work on the numerator only. Okay, if you multiply, you can multiply x times 3 plus x times 3. It's not wrong, but it'll be a big headache for you if you do it, and all of a sudden you won't know what to do after that. So a big suggestion is don't touch the denominator. Just leave it. Got it? So what I'm going to do, what we have now is the x still is going to be x 3 plus x times 3. But now the numerator gets nicer. So what does the numerator become? What is 1 over 3 plus x times 3 plus x times 3? It's very easy. That's a hint. So what's the first term become? 3. And then minus, and what is 1 over 3 times 3 plus x times 3?
3 plus x.
3 plus x. I want to write down something that I see mistakes on. Tell me what my mistake is. Why is that wrong?
Parentheses around 3 plus x.
And if you forget the parentheses, it's completely wrong. So don't forget parentheses when you're doing the subtraction on the numerator. It's a really common mistake in the calculus class. Any questions so far? Okay. What is 3 minus parentheses 3 plus x?
Negative x.
Negative x. Should I multiply the denominator through? Should I go x times 3 plus x times 3 and say that's what, 9x plus 3x squared? What do you think?
No.
No, no. Hopefully you listened to me. I said never touch the denominator. Okay, don't multiply it out. If you do, it'll be your headache. Just let you know that. So don't do it. Got it? Instead, we look at this, and what can I do with the numerator denominator?
Get rid of an x.
Yeah. Okay. And I want to also give you another issue that happens to a lot of people doing wrong algebra, is that you can only cancel a numerator denominator when they're factors. Got it? So for example, this x here on the top, you can't cancel with the bottom x. That doesn't work. Or you can't just cancel these 3 plus x's. That's wrong because of the subtraction. But so that's why we needed to make sure the denominator was in factored form. And if it's not in factored form, you can't cancel. But it is, so now we can cancel. And when you cancel, let's do that. Well, let me, no, just a minute. I'm at the end of the line, so I gotta fix it. There we go, now it's the next slide. So now I can cancel the x's. When you cancel the x, it becomes a 1. This x, you can leave it as a 1 or you can just drop it. Oops. I just canceled. What's the next step?
Plug in.
Plug in. Okay. And that's the thing. Cancel and plug in. Okay. Canceling is, it's usually hard to get to the point you have to cancel. But once you cancel, you smile because plugging in just about always works. And when you plug in, what do you get? It's easy. That's a hint.
-1/9.
Yeah. -1/9. And there we go. There's my limit. Any questions at all on that example? Any questions?
I have a question.
Sure.
How did you get in like the third part, 3 minus 3 plus x? Will you just go over that really quickly? My brain isn't wrapping around it.
Okay, so how did I go from the second part to the third part is what you mean, right?
Yeah.
Okay, so what I did is I said I'm going to take the 1 over 3 plus x here,
Mm-hmm.
and I'm going to multiply by 3 plus x times 3.
Okay.
And the 3 plus x's cancel, and I'm left with a 3. So there's this 3 right here.
Okay.
Then I said I have 1/3 times 3 plus x times 3. And the 1/3 and the second 3 cancel, and I'm left with a 3 plus x.
Okay, got it.
Okay, and then as I mentioned, don't forget, because a lot of people make the mistake, you need the parentheses around the 3 plus x.
Thank you.
Okay, yeah, and that's, by the way, the whole point of having a webinar instead of me producing just a blank video is so you can ask questions. Okay, and I do want to apologize in advance. A week from Monday, so 9 days from today, is going to be a blank video. Sorry about that, but I won't be here. Okay, so that's, I won't be online. But other than that, I'm always going to give you a webinar during regular class times. Sound good? Okay, so now it's time to move on to everyone's favorite topic, trigonometry. So I have a picture, and I copied this from the book. No way I'm going to be able to draw it as nice as the book drew it, because we need this. And just trust me that we're going to need it. So this is a unit circle graph. And what we have here is we have the unit circle. We have an angle. We have the height of this point, or the y-coordinate of this point is sine of theta. We have that this tall area is tangent of theta. Okay, and this all works. And you can play around and you know, I'll let you test it and see that it actually works. Any questions on this picture? Okay, then from this picture, it's going to take some thinking. I wonder if I need to zoom out a bit, maybe. I can get rid of that. No, let's go. Type of view. There we go. Okay, so from this picture, we have the following inequality. As long as theta is small enough, between 0 and pi over 2, theta is between sine of theta and tangent of theta. Okay, the reason for that, first thing, theta has to be bigger than sine of theta. Take a look. If you walk from this point at the bottom up here, that's going to be less walking than going from here and going on this like curvy thing to that point. Because this is straight vertical, whereas this has got vertical and horizontal in it. And if you got vertical and horizontal in it, it's more walking than if you just have vertical. You're going from point to point. Okay, that's the old closest distance between 2 points is a line segment. So that's why theta is bigger than sine of theta. Theta is smaller than tangent of theta. That one's a little harder, and that has to do with the area of this sector piece and this triangle. Okay, the area of the triangle is 1/2 the base times the height. The base is 1. The height is a tangent of theta. So that's going to be 1/2 tangent of theta. And I am going to assume that you're okay with believing me that the area of the sector is theta over 2. So the idea here is that clearly this area here, this big triangle area, is bigger than the sector area. And that's why you get, so theta over 2 has to be smaller than tangent of theta over 2, or theta is smaller than tangent theta. Okay, now you got that in your high school geometry class. Okay, or the class that combines geometry and algebra, if you did it that way. And my guess, maybe I'm wrong, is none of you remember it. Okay, say yes if you remember the proof of this, and say no if you don't. Be honest, and it's okay.
No.
Yeah, I figure it's all going to be no. But say yes if you believe me that it's true, since I'm a professor of math with a PhD in math. Y'all good with that? Okay, and by the way, my specialty in math was called algebraic geometry. So I could do the geometry and the algebra really well. That's what I did. I'm not going to get into the detail of what I do, but you can trust me that this works. And if not, then trust the author of the book. Okay, who also has maybe a PhD in math, probably a PhD in math. And that works. All right, so once we have this, now I can go back to 100%. We don't need the picture, we just need the inequality. Then we could take that inequality and we could divide by the sine of theta. So let's go ahead and do that. And this you all better be able to do is, what is the sine of theta divided by the sine of theta?
1.
1. Okay, and that's going to be less. And by the way, if theta is between 0 and pi over 2, then sine of theta is positive. So dividing by a positive number does not change the inequality. Remember, dividing by a negative number does. But I'm allowed to divide everything by sine of theta because it's positive and have to worry about an inequality change. So we can say 1 is less than, well, we're dividing by sine of theta. So that becomes theta over sine of theta. There we go. Sine of theta. And that is going to be less than, what is tangent of theta divided by the sine of theta?
1 over cosine theta.
Good, good. 1 over cosine theta, because tangent is sine over cosine. So if you divide by sine, you kill the sine. So it's just going to be 1 on the top now over the cosine of theta. Any questions so far? Okay, now I'm going to state what's called the squeeze theorem. And the squeeze theorem says the following. I think I need to make sure it's on a new page because I need lots of space. And that says that if f of x is less than g of x is less than h of x. Okay, which you can see we got a triple inequality here, just kind of in our example, but now this is going to be the theorem. And if the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x. Then, so the idea here is that in the limit, f and h go to the same place. G is always in between the two. So they're getting squeezed because f and h are becoming the same. Okay? And if you're below somebody and you're above someone else, and those two people end up being at the same place, where do you think you're going to end up being? At the same place, right? Does that make sense? So if they're both going to New York and you're always between them, exactly, somewhere between them, then guess what? You're going to end up in New York. Does that make sense? So that means that the limit as x approaches c of g of x is also equal to, in fact, let's just call it L. Let's say the limits are equal to L. Then that will also be equal to L. That's the squeeze theorem. The proof needs epsilon delta stuff. I don't prove it, but you can imagine it's got to be true, right? If you're always below someone, you're always above someone, and they end up the same, then you're going to be there where they are. So in particular, because of the squeeze theorem, now we can say what happens when theta goes to 0. But what happens on the left? If theta goes to 0 on the left, what does 1 become? They hinted this is a stupid question. It's like obvious. What's the limit of just 1?
1.
It's just 1. There's no theta in there. It's just always 1. So the limit is 1. What about 1 over cosine theta as theta goes to 0? What's that going to be?
1.
That's going to be 1 also. Cosine of 0 is 1. 1 over 1 is 1. So guess what? We have the squeeze theorem. Because remember, if you plug in 0 in the middle, you get 0 over 0. And good luck trying to find algebra to do. Do you agree? But we can use the squeeze theorem, And this is important. I'm going to write this as a theorem. And the theorem is the limit as x goes to 0. I'll just call it x so it's easier to type. As x goes to 0, of the sine, and this is how we usually write it because it's more important, the sine of theta, the sine of x, over x is equal to 1. Any questions on this? Any questions? Okay, so this is a big theorem. In fact, here's something I want to do. What'd I just do?
Emphasize.
I made it big and red. Okay, what does that tell you?
It's important.
Seems important.
Yeah, if you don't have this in your brain memorized, this class will go very poorly for you. We're going to be using this the entire course or a lot of the course. Okay, and we're going to be using a big result from this, as you'll see, but not today. So this is an important one. Whereas the squeeze theorem, I'll keep that low in black. After today, we won't use it again. But this limit is going to be used. Okay, you need to know it. Got it? Okay, and again, I kind of proved it. You had to trust me in a few things, but that's the proof. Okay, so now what I want to do is I want to do a couple limits. So let's see what the limit is. I'm going to make this a little bigger. No, it's okay. What the limit is x goes to 0 of sine of 4x over x squared plus 3x. Well, what happens if you plug in 0? What do you get?
0 over 0.
0 over 0. Okay. So 0 over 0 is bad, by the way, right? You do algebra. It didn't work. Okay. But we have a sine of x. We have a sine of 4x, which we'll deal with in a minute. And we have an x squared plus 3x. So the way you deal with this is you do the following. We're going to let u and in calculus, you typically use the letter u when you're doing a change of variable substitution thing. Let u equal 4x. I need this to be theta or x. I can't have 4x. Does that make sense? U is fine. Doesn't matter what letter you have. You know, this formula, the big theorem works whatever letter it is. If it's q, that's fine. If the limit is q goes to 0, sine q over x over q is still 1. Okay, the letter doesn't matter. So what I'm going to do is I'm going to change the letter. So if u is 4x, by the way, x, hopefully you can all do this, is equal to u over 4. You better all be okay with that. Then I can substitute this in. This is a very important technique in calculus, is to rewrite it with a substituted variable. So now I don't have x going to 0. Notice if x goes to 0, so does u. Because u is 4x, 4 times 0 is still 0. So we still have u going to 0, but now we're going to have sine of u over, well, now u is 4x. X is u over 4. So this x becomes a u over 4. And this x also becomes a u over 4. Except it got high. There we go. Anyone lost? Okay, now what I can do is I can multiply top and bottom by 16 just to get rid of the fraction. Just life is a little easier. And when I do that, I have 16 there. This u over 4 squared becomes just u squared. And this 3u over 4 becomes 12u, multiplied by 16, right? Now what can I do to the denominator?
Factor.
Yep, I can factor. Remember, I told you today's all about algebra. Hopefully you're convinced at this point. So I can factor. And I can write that as u times u plus 12. Now what I can do is I can use the big theorem that we had at the very beginning that says you can do any algebra you want as long as things are nice. I can split this up. And I can rewrite this as sine of u over u times 16 over u plus 12. Just basically rearranging. Well, what do we get with sine of u over u?
1.
That's just 1. How about 16 over u plus 12? That's supposed to be easy too.
Just 16 over u plus 12.
Yeah, but u's going to 0, so it's just 16 over 12. And that's my answer. If you feel like it, you can divide by 4 and make it 4/3, but I don't care. Anybody lost on this?
I'm lost on going from sine u over u divided by 4 to the second power. And then going into the
Right here, this one, or?
that part to the next part.
Oh, I just multiplied top and bottom by 16. So you see how the top got multiplied by 16?
Yes, why are we choosing 16? I guess that's what I'm trying to understand.
Oh, I just multiplied by the denominator. When you square this sucker, you get a 16 in the denominator right here.
Got you. Sorry.
You see that? So that's just multiplied by
Yeah.
the denominator. That's a classic algebra thing. Is I don't know about you, but I'd rather not work with fractions if I don't have to. Do you agree?
Definitely agree.
Yeah. So this allows us not to work with fractions. Okay. Could I do it without doing that? Probably, but it's so much easier not to work with fractions. And this made it a lot cleaner. Okay. This last one I can do in a few seconds. How do I do limit as x goes to 0 of tangent x over x? By the way, if I plug in 0, I get 0 over 0. We're used to that. So what can I do? Any ideas? I can write tangent as sine over cosine. And sine x over x, as x goes to 0, is 1. Cosine of x, as x goes to 0, is also 1. So what's the answer?
1 over cosine x.
X is going to 0, though. So you don't want any x's when you're done. Yeah, or how about just 1? You could write 1 divided by 1, but I like 1. So there's a limit is 1. And that's as much time as I have today. So thanks. Have a great weekend. And I'm in office hours now.